2's complement. So AQO would like you to be able to represent negative and positive integers in 2's complement, perform subtraction using 2's complement, and calculate the range of a given number of bits. Okay, let's start. So, first of all, just some terminology here. So we've got LSB on the right hand side and MSB on the left hand side. LSB means the least significant bit. MSB is the most significant bit. Now with 8 bits, you'll notice we go 1, 2, 4, 8, 16, 32, 64, 128, but the most significant bit in 2's complement is negative. Now if you were to scale that down to 7 bits, then again, the most significant bit is turned negative. That's essentially our sign bit. So here it is in 6 bits. Again, the most significant bit is turned negative. There's 5 bits. There's 4 bits. So given the number of bits that are assigned to the number, whatever the most significant bit is, that's the one that is made negative. So here we have a representation of the number negative 110. How did we get to a negative 110? Well, first of all, we start with the negative 128 all the way on the left. And then we add to it 16. We're adding because this is positive 16. And so we're moving up the number line towards 0. Then we add the 2 in, and that lands us on negative 110. Here's another example. So here we have negative 128. So we start all the way down there. And we add on 32, then 16, then 8, then the 4, the 2, and the 1, so 7. And that lands us at negative 65. Okay, one last example. Here we've got negative 128. So that's where we are on the number line. And then we add 64, and then we add 32. And that gets us to negative 32. Now you'll notice that all of these negative representations all share one thing. They all have a 1 in the most significant bit in the first column on the left hand side. So you should be able to spot a negative number in 2's complement because it begins with a 1. So moving on to positive numbers. Obviously we need to set the most significant bit to 0. If we set it to 1, then all of our numbers, no matter what we put in the remaining bits, would always be, the outcome would always be negative. So you must have a 0 in the first column, and then you're simply adding up. So 64 add 16, add 2 gives you 88. In this case, we know it's positive, it's the 0 in the first bit. 32 add 16, add 8, 4, 2, and 1 gives you 63. And the same with this, we're just adding all those up, gives us 127. You'll notice that all these positive numbers are starting with a 0. Another thing to note is because we are, inverted commas, sacrificing that first bit, that lowers the range of numbers that we can access. We're essentially sacrificing the 128, which means the biggest number we can get to, positive number we can get to, is 127, because we've lost access to that first bit. Okay, negation. This essentially means if you have a number, let's say 42, if you go through the process of negation, you are turning that value into its negative equivalent. So in this case, there is a few methods we can use, but I'm going to use the one that I use the most, which is to essentially find the least significant 1 in the number. This, by the way, is just this longer number, just written shorter here. And we're looking from this end, the least significant end, and we're going to find the first instance of a 1. So this is a 0, there's our least significant 1. So this number here. The next thing we need to do is flip the bits to the left of that least significant 1. So everything left of this arrow is flipped. So if you check this out, the first 2, including the first significant 1, or the least significant 1 I should say, we flip that 0 to a 1, flip that 1 to a 0, 0 to 1, 1 to 0, and so on. This is now the negative representation of positive 42. So this is negative 42. Okay, so there we have negative 42. Pretty simple. Okay, here's some examples for you to have a go at. So there is the positive number. What would its negative equivalent be? So you would start by finding the least significant one, which is in the twos column here. And then everything left of that, we flip. Here's another. So again, if we look at this, we're finding the least significant one. It just happens to be the very first one in the ones column. So everything left of that, we're going to flip. Here's another one. Again, the first number is the least significant one all the way on the right. So everything left of that, we flip. And for this one, we have to go 1, 2, 3, 4, 5 places in to hit our least significant one. So we're going to flip these 3. That's exactly what happens. Okay, AQA throughout the spec refers to numbers as being smaller or larger. So smaller just means we're heading into the negative numbers, larger up into the positive numbers. Okay, calculations using 2's complement. Now, one thing to be aware of when we move on to some other examples is because that left hand most significant bit is a sign bit, if we accidentally do an overflow error into that sign bit, we can completely flip the number and the value of the number. So if we look at this addition here between these two numbers, we know that these are two positive numbers and that the answer is positive because we've got a 0 in the left-hand column. So that's fine. That works out. If we do this addition, this carrying of ones carries into the sign bit, okay, the most significant bit. That means that we flipped the addition of these two positive numbers, and the result is a negative number. So this is a sign bit affected. In this case, we have no error, and in this case, we have an error. We've essentially output the incorrect number. Okay, now when we're doing subtraction in 2's complement, we're essentially doing addition. So we're adding a negative number to a positive number. That has the same effect as you and I might do a subtraction on paper. So up on the right hand corner here, we've got the calculation that we're doing. We're trying to do 123 subtract 33, and we expect the answer to be 90. So the first thing we need to do is, and again, all of this is the kind of detail you need to show in exam answers. So we need to show that we can do these steps. So the first thing is we convert the minuend, so the top number, into a positive 2's complement number. So we need to make this into a 2's complement number. So there's that. Okay, so this is the representation of 123. Next up, we need to do the same to the subtrahend. This is the bottom value, this guy here. So first we do the positive representation of 33, because that's reasonably simple to do, which is this. So this is 33, and then we can negate it. So then we find the least significant one, and we flip the bits to the left of it, which gives us this. Okay, so this was our least significant one, and so we flipped all the bits to this side. So we've now got negative 33. With that, we can now do our addition, which is the same as doing a subtraction. So we're adding the negative number to the positive number. So we've got our representation of negative 33. Now let's do the actual calculation. So there's 123. There's negative 33. This box is for my carries, and this is where the answer is going to go. So if we start on the right-hand side and we do 1 add 1, we get 0 carry 1. 1 add 1 add 1 is 3, so 1 carry 1. Then we've got 0 carry 1, 1 carry 1, 1 carry 1, 0 carry 1, 1 carry 1, and then we've got 0. And what we do is we just completely discard any carries from the calculation. Okay, so we would normally carry the 1 and then it would be 1, 0, 1, 0, 1, 1, 0, 1, 0, but we're just going to get rid of that carry. And this is our answer. This is 90. So the steps are convert the top half, convert the bottom half, positive representation, negate it, so flip all the bits to the left of the least significant one, and then do an addition, discarding any overflows from the most significant bit onwards. Now the last thing to look at is the range of numbers we can have given a number of bits. So here we have a 7-bit number. If we look at this, the most negative number we can have is simply achieved by putting a 1 in the most significant bit. So if we put a 1 in there, we get negative 64. So the max value versus the min value, the max value is, in this case, plus 63. We get that from adding all of the positive values together. That's as large a number as we can get. The most negative, or the minimum value, is simply achieved by putting a 1 in that most significant bit, which gives us negative 64. Now if we look at a 4-bit equivalent, it's the same principle. So the max value we can achieve is 4 add 2 add 1, all of the positive values, and the minimum value is achieved by just simply putting a 1 in the first or most significant bit. So plus 7 all the way down to negative 8. So with that in mind, let's go through a few examples of this. Calculate the range of given numbers of bits n. So here's the formula to work out the maximum value and the minimum value. So there's a formula for the maximum value, and there's the formula for the minimum value. So what does this actually mean? So if we take the 4-bit number we were looking at, and we substitute in n with 4, we've got 2 to the power 4 minus 1. So 4 minus 1 is 3, so 2 to the power 3, and then we subtract 1 from that. That gives us plus 7. So 2 to the 3 is 2 times 2 times 2, which is 8, and then we subtract 1, we get plus 7. So that's the maximum value. To get the minimum value, we substitute in the number of bits into n, and this is 2 to the power 4 minus 1. So again, it's 2 to the power 3, but we're going the other way. So negative 2 times negative 2 times negative 2 gives us negative 8. So the range in 4 bits is from plus 7 to negative 8. Now as we go forward, you'll start to see a pattern emerging. So here's 5 bits, same thing. So we just plug in the 5 bits into n, we calculate that, and then we do the same for the other side, and we get that. So let's move on. Here's 6 bits. Here's 7 bits. So it's the 7 minus 1, so 2 to the 6, subtract 1, negative 2 to the 6 gives us that. And lastly, 8 bits. Okay, so if you look across all of these, plus 7 to negative 8, plus 15 to negative 16, plus 31 to negative 32, plus 63 to negative 64, plus 127 to negative 128. Thanks for watching.